Hello, good evening, everyone, and welcome to this ICTS very special lecture of ours, the ICTS Infosys Chandrasekhar lectures. I'll just say a couple of words about them. These are our flagship lecture series. We have the Chandrasekhar lectures, the Turing lectures, and the Ramanujan lectures in the Chandrasekhar in physical sciences, Turing in biological and computer science and engineering sciences and related topics, as well as Ramanujan lectures in the mathematical sciences. And the format is to have one lecture in this series. Usually it is the first, but in this particular case, the order was sort of flipped, but it doesn't matter. One of the lectures is aimed at a broader scientific audience as a colloquium level lecture. And the others are, of course, technical lectures, always embedded in a discussion meeting like this. And we have had a number of very illustrious speakers in this series. And it's a great privilege to have Professor Gian Giudice, whom we have all heard, many of us have heard in the last couple of days for his brilliant lectures, but now we'll hear him talk about simplicity, complexity, and the universe. But I will hand it over to Spenta Wadia, the founding director of ICTS, to introduce the speaker and chair the event.
Good afternoon, everybody. It's a great pleasure and privilege for me to introduce Gian Francesco Giudice, whom I know for many years now, myself being a CERN associate for many years, and very proudly so. Gian graduated from the University of Padova in 1984. Did his PhD from CISA in Trieste in 1988, and his advisor was Riccardo Barbieri, everybody knows. And then he was a postdoc at the Fermi Lab for a couple of years. And then he was a postdoc with Stephen Weinberg at the University of Texas at Austin. And after a brief tenure at the INFN, he moved to CERN in 1993, and he has been there since then. And currently, he is the head of the theory division at CERN. A very important leadership position in particle physics. So Gian has made deep and influential contributions to the physics of the Standard Model and beyond in a wide range of areas, which includes pioneering contributions to gauge-mediated supersymmetry breaking, minimal flavor models, large extra dimensions, and split supersymmetry. The discovery of the Higgs boson at LHC with a mass of 125.35 GeV led him to the study of the stability of the electroweak vacuum and its criticality. His present work, which we heard in the first lecture, deals with a dynamical systems approach to quantum cosmology and the importance of dynamical attractors in the multiverse. Being at CERN, he is actively involved in supporting the experimental activity at CERN and also worldwide. He's a member of the LHC Experiments Committee and the European Committee for Future Accelerators, and a coordinator of many study groups, including LEP, Tevatron, Neutrino Factory, LHC, CLIC, etc. He's also an active person in science outreach and science popularization of the great ideas and achievements of theoretical and experimental physics, particle physics. He has written a popular science book called Zeptospace Odyssey, which is all about LHC and particle physics. It's been translated into several languages: Italian, German, French, Spanish, and also Korean, I noticed. So for his outstanding contributions and achievements, he has won several accolades: Academician of the Instituto Veneto di Scienze, Lettere ed Arti, and of Accademia Galileana. I hope I got the pronunciation. Thank you. And he has also been awarded the 2013 Jacques Solvay Chair in Physics. And with this, I would like to invite Gian to deliver his Chandrasekhar lectures on simplicity, complexity, and the universe. Gian, please.
Nima achvanake tumba danya vanagalu nanage tumba gaura vavide. So although it would be much easier for me now to continue in Kannada, let me switch to English simply for your benefit, because I know that we have a mixed audience, okay? So as I was saying, I'm greatly honored to be here today and give the Chandrasekhar lecture. Subramanian Chandrasekhar is a hero for generations of physicists. And in him, one finds also human qualities, those human qualities that enrich the role of a scientist. First of all, he is internationalism. Chandrasekhar, the man and the scientist, is a blend of three cultures. Above all, he is Indian because of his upbringing and cultural heritage that he kept during all his life. But he was also highly influenced by English culture during his Cambridge years. In particular, he kept all his life the custom of wearing impeccably elegant Western clothes. And Goldberger told a story of when they were both in Los Alamos and decided to go, in the evening, they decided to go for a hike in the mountains. So in the morning, Chandrasekhar shows up wearing a beautiful, well-tailored suit, ready for the hike, okay? So Goldberger recalled, so I loaned in a pair of khaki jeans and a short-sleeved shirt. I had worn these clothes myself, but on him, they were just absolutely transformed. There is something so unbelievably elegant about him as a person. Then he spent most of his scientific life in the US and absorbed the American culture, being also engaged in political life. So Chandrasekhar embodies the international spirit of science, of our community, being a blend of the East, the West, and the Far West. His second human quality is his cultural breadth. He felt that science is only one facet of the human endeavor of understanding nature, and he was deeply interested in all forms of art. Science is a perception of the world around us. I feel that an appreciation of the arts is a conscious, disciplined way, might help one to do science better. In particular, he loved literature and became an exquisite writer himself. His book, Truth and Beauty, which I read before coming here, is really a jewel. And he says, my interest in literature began in a serious way in Cambridge around 1932. I used to devote most of the 2 to 3 weeks between terms to the study of literature. He was a very systematic person, okay? He showed from the very beginning. The third aspect is his deep aesthetic view of natural reality and science. It is indeed an incredible fact that what the human mind at its deepest and most profound perceives as beautiful finds its realization in external nature. What is intelligible is also beautiful. And Chandrasekhar's words are still guiding us in the pursuit of understanding nature at its deepest level. So modern science starts with the discovery of a relationship between the physical world and an abstract world of pure mathematical forms. The link between the idealized world of mathematics and the world of physical reality is given by the physical laws. So nature is governed by universal laws that can be expressed in the language of mathematics. And this astounding discovery reveals a pattern, an order in nature. Science has shown that, that an order in nature is not an illusion of our perception or a construction based on philosophical or religious beliefs or a creation of our abstract mathematics, but is reality itself. And this, for me, is the biggest mystery that confronts human mind. The reason for the existence of physical laws, of an order in nature, is probably a mystery that goes beyond even the reach of science. And the apparent chaos of natural phenomena hides a surprising inner simplicity. We can make sense of nature and we can make progress in science because we can deconstruct physical phenomena and study them in isolation. And this procedure of decomposing reality goes under the name of reductionism. In simple words, reductionism means that we can describe a phenomenon by considering only a limited range of distance scales and ignore anything that happens at smaller scales, right? It's, we can write down an effective theory which describes only the degrees of freedom relevant to that particular phenomenon, while all the information about what happens at smaller scales can be embedded in a few free parameters. And this ability to separate systematically reality in subsequent layers of knowledge is what allowed physicists throughout the history of science to make progress in the understanding of nature. Indeed, Newton didn't need to know about the atomic structure of matter to compute the orbit of the moon around the Earth. And Bohr could compute the atomic levels without knowing about the existence of quarks and gluons. By descending this ladder of multiple layers, we expose the secret simplicity of nature. And yet the world around us is complex. The mechanisms that generate life, biological organism, the perception of consciousness and free will are not describable by fundamental physical laws because they belong to the land of complexity. We will never be able to understand a tiger's behavior when the tiger is hunting, or a volcano eruption, or the functioning of a computer, just by listing the atoms that form them. So a complex system is much more than the sum of its parts. A complex system is governed by emergent physical laws, in principle deducible from the fundamental laws that govern the constituents, but in practice completely independent. And this is the most extraordinary marvel of nature, the coexistence between simplicity and complexity. So complex systems develop in an almost magical way emergent physical laws that acquire a life of their own. At first sight, completely unrelated to the microscopic structure of the system. And yet the complexity, apparently chaotic, hides a rational scheme of simple constituents governed by fundamental laws. There is a hidden logical thread that connects emergent and fundamental laws, creating a fabric of reality suspended between simplicity and complexity. And this interplay between simplicity and complexity is really the marvel that makes natural phenomena so fascinating, both when studied by scientists who deduces the inner beauty of their mathematical structure, or admired by artists who are able to express the beauty of the emotional impressions. So we have discovered a ladder in science of some subsequent layers, which reveal a higher degree of simplicity as we probe smaller and smaller distance scales. And the standard model of particle physics, together with general relativity, is the framework that represents the most fundamental layer of reality we know. It is the framework that realizes a conceptual synthesis in which all known forms of matter and forces are described by a single principle. And we call this principle the gauge principle. And it corresponds to the requirement that the theory remains invariant under a set of mathematical manipulations. So the gauge principle is at the heart of the interplay between simplicity and complexity. So suppose that you've been given the task to create the universe. So you will be facing an alternative, right? Do I privilege simplicity or complexity? And if you go for simplicity, you can take simple building blocks and write down simple and essential physical laws. You will create an elegant universe based on pure principles, but so simple that probably is not much more than a construction of Lego blocks, okay? It's hard to believe that you can create a universe complex enough to host complex phenomena such as life. The alternative is to go for complexity and write down different physical laws for different phenomena. Now, your creation allows for elaborate structure, but lacks an underlying logic. So your universe is just a jumble of disconnected elements. So what would you choose, simplicity or complexity? Well, nature has chosen both. Simple fundamental principle and emergent complexity. A secret behind this highly non-trivial solution that nature has chosen is gauge theory. The gauge principle is, from a conceptual point of view, incredibly simple. And yet, in spite of this profound conceptual simplicity, gauge theory is incredibly rich. The same logical principle underlying gauge theory can lead to a long-range force, such as electromagnetism, or to confinement, like in strong interactions, or to short-range forces, like in weak interactions through the mechanism of spontaneous symmetry breaking, or to gravity when applied to space-time diffeomorphism. So the unbelievable richness of gauge theory also becomes evident when we explore its vacuum structure. Instantons, sphalerons, theta vacua, chiral condensate, gluon condensate are all expressions of this emerging complexity of the vacuum of gauge theories. And at finite temperature and finite density, gauge theories exhibit a variety of new phenomena and a complex phase diagram. So gauge theory, it really fuels the miracle of emergent complexity out of conceptual simplicity. But as we move away from particle physics and we observe nature with less and less resolution, going from nuclei to atoms, molecules, cells, and biological organisms, complexity emerges over simplicity. The fundamental description becomes more and more useless from a practical point of view. And knowing the fundamental interactions of quarks is not particularly useful if you want to fix your car or if you want to understand why you're falling in love. Complexity takes over for those phenomena. So is complexity increasing forever when we go at larger distances? Well, surprisingly, the answer is no. When we look at the universe at distances larger than about 300 million light years, so beyond the scale of galactic superclusters, we find a surprise that the universe looks uniform. And this is fully confirmed by the observation of the cosmic microwave background, which is extraordinarily uniform across the entire sky, showing almost precisely the same temperature in the full frequency spectrum. So simplicity re-emerges out of complexity when we go to very large distances. And this is the reason why the fundamental physical laws that we derive from particle physics then become important again when we study the universe at very large scales. So fundamental physics addresses simultaneously the very small and the very large, but becomes ineffective in between. And the simplicity of the universe at large scale may sound very reasonable, but actually it hides terrible, complicated puzzles. The simplicity of the large-scale universe may seem just an innocent observation, but is actually extremely perplexing. Why is the cosmic temperature so uniform? Now, things we know reach the same temperature when they go in thermal equilibrium. So it's not surprising that the chai in your cup has all the same temperature. But when the cosmic radiation was formed, about 380,000 years after the Big Bang, the universe was too young to have reached thermal equilibrium. So it's like to find that your chai has the same temperature as a cup of chai left by an alien on Pluto. How can it be? And what made the uniform space to expand? What caused the Big Bang? What was the engine that set in motion this massive expansion of space that followed the Big Bang? And the answer to all these questions lies exactly in the deepest level of simplicity. It lies in the physical laws of the microscopic world. What could be the cause of the Big Bang? When we consider the universe at large scales, there's only one force that really matters, and that is gravity. But the force of gravity is always attractive. Gravity makes things fall on Earth. It keeps the Earth in its orbit around the sun. It keeps stars bound inside galaxies. So gravity can cause contraction of matter, or at best, slow down an initial expansion. But an attractive force like gravity cannot cause an expansion. Well, this is true in Newtonian gravity, but not necessarily in general relativity, the Einstein theory of gravity. According to general relativity, there is one exception, one possible source of repulsive gravity, of anti-gravity, if you wish. And this is vacuum energy. So vacuum energy is an amount of energy present in the fabric of space-time, even in the absence of any kind of matter or radiation. And unlike other forms of energy, it has the property, the singular property of appearing identical to any observer in motion, which is exactly like empty space. So in this sense, it's really indistinguishable from empty space. May seem odd, but according to general relativity, vacuum energy anti-gravitates and gives rise to a repulsive gravitational force. Now, anti-gravity may appear as magic, but phenomena associated with vacuum energy are not simply a creation of the imagination of theoretical physicists. The study of the microscopic world has shown that vacuum energy is part of the physical world. It is at the root of the phenomenon of superconductivity, as well as the Higgs mechanism. And this has been proven to exist in the real world by the discovery of the Higgs at CERN 10 years ago, almost exactly. So theoretical physicists now speculate that some new particles similar to the Higgs boson could have produced a large amount of vacuum energy in the early universe. And the repulsive gravity due to the vacuum energy could be the engine that generated the initial expansion of the universe. Indeed, vacuum energy can give rise to a powerful expansion, which physicists call inflation. And theoretical calculations show that inflation can stretch space so fast that in a billionth of a billionth of a billionth of a billionth of a second, anything as small as a part of space as small as a COVID-19 virus can become as large as the observable universe today. And this prodigious expansion caused by inflation created exactly the right initial conditions of the universe that we need to explain what we observe today. So the universe is expanding because of this initial kick caused by vacuum energy, and the universe is hot because at the end of inflation, the vacuum energy locked in the inflationary field was released in the form of thermal energy of a dense gas of particles. So the answer that inflation gives to the Big Bang is that there was no bang at all. The Big Bang is not an explosion in a point in space, but rather a phase transition that occurs almost simultaneously in a large region of space. Just like a frozen lake that suddenly melts almost uniformly everywhere. So before the Big Bang, the universe was cold, dark, and filled only with vacuum energy. And after the Big Bang, the universe is hot and filled with high temperature matter and radiation. And the universe is almost perfectly uniform because of the super fast expansion. It's like when you stretch an elastic fabric. No matter how you start, after stretching, the fabric looks flat. This extreme uniformity of the universe predicted by inflation, however, comes with a puzzle. This inner simplicity actually corresponds to a state of minimum entropy. So we are used to think of a uniform gas as a state of maximal entropy, right? It's a state in thermal equilibrium, and so it's a final state of a system completely unordered. Well, in gravity, things work in the opposite way. A uniform distribution is a highly ordered state, while all matter collapsing into a black hole is the final unordered state with the maximum possible entropy. So starting with a state of low entropy is exactly what you want to create a universe that can host complex phenomena. If you're already starting with the maximum entropy, well, you're not going to generate any complex phenomena because you are in thermal equilibrium already. So you're not going to generate life. Gravitational collapse can cause structures to be formed out of initial unhomogeneities. But gravity cannot form structures out of perfect uniformity. So the question is this perfect simplicity predicted by inflation then incompatible with the complexity that we observe in our universe. And here comes really the most amazing part of the story, showing a link between the physical universe at the largest scales and nothing else than quantum mechanics. Remember that Heisenberg's uncertainty principle states that certain physical quantities cannot be precisely determined. And the vacuum energy that caused inflation is no exception to the rule, and so it cannot be perfectly uniform. Fluctuations must exist at very small distances. In ordinary life, these fluctuations, yeah, they exist, but they're too small to make any difference for our senses. But remember that inflation stretches space enormously. So as a result, these tiny quantum fluctuations are amplified and end up covering enormous distances. So inflation mixes small and large distances, making the physical laws of the micro world to govern the universe at the largest scales. And the primordial quantum fluctuations in the vacuum energy of the universe can leave their marks on matter, radiation, and geometry. So for instance, they can affect the cosmic microwave background, the radiation that we observe today in the sky. And because of the presence of the original quantum fluctuation stretched to enormous distances by inflation, the cosmic microwave background cannot be perfectly uniform. And indeed, experiments have revealed that its temperature varies at the level of 1 part in 100,000. So this figure shows the temperature variations as a function of the separation angle in the sky. And the solid line is the theoretical prediction from inflation, and the points are the experimental data. Well, I don't need to enter into details. I think that this figure really conveys the fact that the agreement between theoretical prediction and astronomical observation is really striking. So quantum fluctuations affect not only radiation, but matter as well. So the quantum fluctuations created during inflation become the seeds for the formation of galaxies in the universe. And then gravitational collapse makes these initial seeds grow into the pattern of galaxies that we observe today. And again, the comparison between theoretical calculations and astronomical observations is fantastic. So it's just like animal fossils buried inside the rocks that preserve the traces of creatures that lived long before humanity appeared on Earth. And in the same way, the distribution of galaxies in the sky is a gigantic fossil hiding the traces of the microscopic ripples of the vacuum energy that set the universe in motion. So remember it next time that you watch the sky at night, especially with your lover. You're really going to impress if you tell your partner that you are watching microscopic quantum fluctuations that remain hidden for billions of years in the folds of the universe. It's really a romantic scientific story. Inflation is really the culmination of the profound link between the microscopic world of quantum mechanics and the immense distances of the cosmos. The simplicity of the micro world determines the simplicity of the universe at large scales. However, gravitational collapse transforms the pattern of these quantum fluctuations into the complexity of galaxies, stars, and ultimately life. And that is what transforms this original simplicity into today's complexity. And this is really this ultimate realization of the complementarity of simplicity and complexity, which really manifests this unity that we understand in nature. So I've painted a picture of reality in which simplicity emerges at very small and very large distances, while complexity rules in between. Is this the end of the story? So to answer this question, we must go beyond the boundaries of the observable universe, beyond the cosmic horizon. Now, what is a cosmic horizon? Since the speed of light is finite, and the time since the Big Bang is finite, we can receive physical information only from a finite region of space. It's not a limitation of our instruments, but it's really a consequence of the laws of special relativity. And it's the same that happens for sailors in a ship, right? They can see the ocean up to their horizon, but not beyond. And it's not a limitation of their optical instruments, but really, but it is a physical consequence of the terrestrial curvature. So what happens beyond the cosmic horizons is inescapably invisible to us. But in the same way as a sailor, as a smart sailor cannot think that the ocean ends at its optical horizon, there's no reason why the universe should end at the cosmic horizon. Actually, inflation gives good indications that the universe will extend much more beyond the horizon, since space is stretched enormously during the inflationary epoch. So does uniformity of space extend forever, even beyond what we can see with our instruments? Well, inflation gives a very interesting answer to this question. So consider a region of space subject to inflation, and this is represented by this gray box. So inside the box, space expands furiously, fueled by inflationary vacuum energy. But because of the stochastic evolution of the inflationary field, some parts of that region will reach the conditions where vacuum energy vanishes, inflation stops, and a Big Bang happens. So as an example, suppose that after a unit of time, inflation stops in a fourth of the initial region of space. And this is the white region. So the white region is a region in which inflation has ended and a Big Bang has happened and a thermal universe has started. In the rest of space, inflation continues and space keeps on expanding. And again, after another unit of time, 1/4 of space undergoes a Big Bang and the rest keeps on expanding exponentially and so on. So in summary, the fate of the universe is determined by two opposite effects. One is expansion that makes inflationary regions grow. And the other one is the inception of the Big Bang that stops inflation. Whether inflation stops everywhere depends on which of the two effects is dominant. It's like for our animal population. If mortality dominates over natality, then the population gets extinct. But if natality dominates over mortality, the population grows continuously. We still don't know which of the two effects dominates, because we don't know the details of the theory of inflation. But there are good indications that the evolution of the inflationary vacuum is sufficiently slow to make sure that somewhere in the universe, there are always regions of space where inflation persists. In other words, inflation is eternal. And this has dramatic consequences for the global structure of the universe. If we could fly out of physical space and watch the entire reality beyond our cosmic horizons, we would have a spectacular view of the universe. the universe would look like a patchwork of regions of space in hectic expansions, just like an ocean caught by a violent tempest. But here and there, little islands of space emerges where inflation ends and its energy, the vacuum energy, is converted into hot gas. And those are Big Bang events. And Big Bang events occur continuously in different places at different times. Each of these islands is a new universe. And physicists have invented the word multiverse to describe this complex reality. So eternal inflation is offering us a portrait of physical reality which is completely different than what we could have imagined by extrapolating what we can see with our telescopes. The idea that the universe is uniform at large scales is only an illusion of our limited point of view. We live inside a bubble of space, unaware of all the action that is happening beyond. Our universe is only one element of an immense multitude. And the Big Bang is not a special event in the cosmic history. Big Bangs happen continuously, like drops of water that fall on the ground, and they will keep on happening forever. So throughout history, our perspective of the cosmos has progressively changed with a succession of Copernican revolutions. We have learned that the Earth is not the center of the universe, but rotates around the sun. The solar system is not the center of the universe, but rotates every 230 million years around the Milky Way galaxy. Our galaxy is not the center of the universe, but it's only one of thousands of billions of galaxies that populate the observable universe. So the Earth is not any special point of the universe. And for me, the multiverse is the ultimate step of the Copernican revolution. Our universe and everything that we can see is only a small island of an immense and much more complex reality. So some physicists have little sympathy for this picture, but I feel exactly the opposite, as you have understood by now. And the idea of a perfect universe, simple in its extreme uniformity, for me strides with the spirit of the Copernican revolution and with what we have learned about nature. Nature prefers simple fundamental laws, but complex manifestations. And this is what we see in the physical reality around us. And it's not surprising if this is what happens in the universe at the largest possible scales. For me, instead of a perfectly uniform universe, it is much more appealing a picture of the cosmos in eternal evolution, where there is no universe is special, but only part of an immense population of individuals who are born and die in a cycle of life. In the multiverse, there's nothing absolute or perfect, but only ever-changing space and matter. And this picture seems to me much more in tune with what we have learned so far about nature. In the context of string theory, physical parameters vary in the huge landscape of the vacuum structure of the theory, and therefore are determined by accidental circumstances. This means that each of that universe of the multiverse is likely to have different physical parameters, coupling constants, vacuum energy, masses, and even number of space dimensions. These differences seems very innocent, but in practice, they make a huge impact on the way physical reality appears. Each universe will really look completely different and apparently following distinct physical laws. But we shouldn't think that the multiverse is just random chaos where anything can happen. The basic structure of the physical laws corresponds to an inner simplicity, which is, however, hidden by the complexity of the multiverse. So once again, nature is simple in its principles, but complex in its manifestations. The multiverse changes completely the rules of the game in the quest for the final theory. Searching for a final theory in the universe may be an illusion, so much as trying to understand the geography of a beach by studying a single grain of sand. The rules of the game must be changed, and probability enters the game. From this point of view, physicists today are in a situation similar to the beginning of last century, when quantum mechanics forced physicists to abandon their belief in perfect determinism and in the idea that the universe is just a simple clockwork toy. And there is, however, a big difference, unfortunately, and the probabilistic laws of quantum mechanics could be tested by repeating experiments in an indefinite number of times. On the other hand, the probabilistic laws of the multiverse can be tested only in one universe, ours. And this makes the job of multiverse explorers terribly complicated. And understanding the rationale behind a probabilistic interpretation of the multiverse is a daunting task. And here during the ICTS workshop, I presented some ideas on how to tackle the problem. And the ideas were that taking inspiration from complex phenomena that we normally observe in nature, I've proposed that criticality may play a decisive role. Out of all possible universes, there is an overwhelming majority of universes that are close to critical conditions. So according to this logic, dynamics drive physical parameters towards critical conditions. Criticality is attractive. So let me get to my conclusions by summarizing what I said. The interplay between simplicity and complexity is what causes nature to be so beautiful in the essence of its principles, and so interesting in the intricacy of its phenomena. And the complementarity of simplicity and complexity is really, for me, one of the most fascinating mysteries of the physical world. Nature prefers simple principles, simple fundamental principles, and complex manifestations. We have discovered that simplicity dominates reality at very small distance scales, in the quantum world of particle physics, and at very large distance scales of the size of the observable universes. And in these domains, we can hunt for the simple fundamental laws with particle accelerators at small distances and cosmic surveys at large distances, leaving everything in between to our colleagues that are interested in the science of complexity. But the multiverse is telling us a different story. Complexity is reappearing when we look at the universe beyond the boundaries of the cosmic horizons. And once again, the manifestation of nature is complex, even in a regime where we were expecting, just by extrapolating astronomical observation, we were expecting simplicity to rule the world. So simplicity and complexity are not opposite concepts, mutually excluding. On the contrary, simplicity and complexity are complementary in the description of nature, and their relative prevalence changes with the length scale, but repeats itself in a cycle that could be infinite, like an eternal samsara. So this picture changes the strategy with which we have to continue our exploration of the fundamental laws of nature. If I have another minute, I know I'm running out of my 45 minutes. If I have just 1 minute, I want to tell you a story to conclude. And that is a story that Chandrasekhar liked to tell. And I've read it in one of his biographies. So the story is the following. And this is really, Chandrasekhar sort of was repeating the story over and over because there's an interesting moral. An old farmer was busy planting mango seeds. And a king arrived in the area, and seeing this old man started to laugh loud and went there and asked him, "Good man, how old are you?" "Almost 90, my lord," replied the farmer. Still laughing, the king asked, "And do you expect to eat the fruits from the tree that will grow from the seeds that you are planting?" "Of course not, my lord. But I ate the mangoes from the trees that my father and my grandfather planted. Now, I hope that my children and my grandchildren will be able to eat the fruits from this tree." The king was so impressed by this answer that he gave 4 gold coins to the farmer. So once the king left, the old man looked at the gold coins in his hands, chuckled, and whispered, "And he thought that I wouldn't get anything out of those seeds?" So this is, I think it's, I don't know what Chandrasekhar thought about it or what he wanted to say, but for me, this is how science works. Theoretical ideas and big experimental projects are part of a long journey that humanity has undertaken. Each scientist is part of this large endeavor and is making only a small step. But that doesn't mean that along the way, even that small step, you don't get rewarded with unexpected gold coins of knowledge. So science is facing new ideas that can reshape our view of the universe, but we have only scratched the surface of a new mysterious world. The simple is the seal of the true, and beauty is the splendor of truth. Dhanna Vadya Galu.
Wonderful, wonderful.
My pronunciation of Kannada is not as good as your pronunciation of Italian, I must say.
Understandably. Okay, so before we go for questions, our usual custom is to present you with a small memento, which I hope you like.
Oh, thank you very much. I really appreciate it. Thank you a lot. Yes, yes, absolutely. I'm sure everybody's curious, so I'm doing it for them because I can check it in my, the guest room easily. And whoop, ooh, this is wonderful. This is wonderful. I have. Thank you very much. In my office, I don't know if you've been in my office.
I have.
Oh, you remember that I have a place where I put all the memories from various science-related trips, and especially from various institutions. And so I like it very much. And this will be in a prominent place. It's really wonderful. Thank you. So thank you very much to all of you.
You'll take a few questions?
Absolutely.
Yeah. Okay. Questions?
I also take questions in Kannada, if you wish. It's been a long day for everyone.
Yes.
This is a question from an expert. Now.
Maybe a little provocative. So one of the criticisms that I've heard since my student days of the multiverse paradigm, that there are more universes than ours, is the apparent lack of falsifiability. Would you like to comment on what your take is?
I mean, of course, you are touching a very delicate point, that it's going beyond the cosmic horizon, is stepping into a territory that could be considered non-scientific. And as I also expressed in one of my lectures, one has to be cautious about that. I think it is important to explore and investigate, and also what we define testable and untestable, it really changes with time. And as I was stressing, there are most of the phenomena in particle physics, most of the discoveries made at CERN, they're actually dealing with phenomena that cannot be seen directly. Even if, in principle, you could see a time scale less than 10 to the minus 22 seconds, which is a time scale of lifetime of a Higgs boson. In practice, there is there's no known electronics that is sensitive to those time scales, and I can't even imagine in the plausible future that it will exist. So even there, we are not observing the phenomena, but we are observing the consequences. This is what's happening everywhere when we're dealing with physics at the extreme. So we should get used that we have to go into regimes which are not testable in the sense of Newton, but where with our minds we can understand the consequence. Now, of course, the next question is, so what are the consequences of the multiverse? And there are some that's been suggested in the literature, like a scattering of the collision of bubbles of universe, leaving marks in the CMB, or the collapse of universes, leaving the marks of black holes. However, these are honestly a little bit far-fetched in the sense, yes, experimentalists are looking for them, but we cannot predict if they happen, and are probably very unlikely to happen. So for me, the way forward is really by theory. So theory now should play the role of clarifying the issues. So for instance, clarifying what is that drives inflation, what is the inflaton, what is the theory of, and then we can check, is eternal inflation really happening or not? And testing that would be the case is one step, which is very important. The next step is to strengthen our understanding of quantum gravity, so that now instead of just making wishful thinking, we can really test our ideas. And even if we don't have that, we can start playing games. And one of the games, I explained it in my lecture, where we can make certain assumptions, and within certain frameworks, we can get certain assumptions, certain conclusions. It's, I repeat it, I said it also in the lecture, right? It's like saying, what are the consequences of quantum field theory? Well, it's a little bit of a what are the experimental consequences of quantum field theory? Well, you have to specify what is the model. So I can answer, what are the experimental consequences of the standard model of a specific theory. So clearly, even, asking, so how do you test the multiverse? I would say, how do you test a specific model of the multiverse? That's where we should go. That is more realistically. But of course, the difficulty is now to construct models without having a firm theoretical background of what's happening at that scale. But for me, that's not a reason to give up. Actually, it's even one more reason to continue the exploration, which should come from many, many directions, certainly from particle physics, cosmology. But if we're really dealing with the physics of complexity, maybe even from other directions which are new. It's an incomplete answer, but because that's a real state. I would cheat by telling you, well, you know even more than me on this subject. So,
Yeah.
If someday we could produce, say, a Planck temperature in some region of the universe or in the lab, wouldn't we see some consequence of the multiverse, other universes?
if we could see, sorry.
If we could produce a region where you have achieved Planck temperature.
I mean, I don't know in what experiment can we do that.
Well, I mean, in principle,
Like,
if
so
we
just
have a
in
very high energy
principle, just in
accelerator,
principle.
we could.
I think that's not necessarily sufficient, right? Because you should really recreate the state of inflation. It's a collective phenomena that you want to recreate. It's not just sufficient to get the energy. I mean, even if I get to a super Planckian energy, I mean, I don't know what you're thinking. I mean, if you think of scattering of particles, super Planckian energy, that is not sufficient, right? You should really recreate all the collective phenomena that produce inflation. And in that case, you could create the multiverse, but please don't do it because it would not be a good thing for our environment.
Yeah, I mean, what I had in mind is more like a quark-gluon plasma, but with Planck temperature.
Yes, I mean, it's science fiction, but probably yeah. I mean, the question that I'm thinking is if you could really recreate the phase transition that led to inflation. Probably yes. Probably I would say yes. You have to think more, however, if there's not, it's because sometimes it's not that trivial, right? Because sometimes even if you reach temperature either in the phenomena, you don't have the conditions. But I imagine that you could go back in time, let's say, and if you could have a quark-gluon plasma beyond that is hotter than the reheating temperature, then I imagine that you could go backward. I have to think a little bit more, okay? I don't want to be too hasty, but it's rather unlikely to do it. It's nice, but it's a nice, interesting question that I never thought of, just as a principle. I don't think it's something that we can suggest to experimentalists, but it's a provocative, it's an interesting thought.
Just an extension on this. But that is still not a test of multiverse, is it? It's just something that will tell us what would have happened if we had quark-gluon plasma at large temperature in our universe.
Right, but the idea, I imagine, would be, if you're going back to a state, and if you create, even it could be a microscopic state in which you really go back and create a state of inflation, that will start inflating. Okay, and so then by itself will start inflate. And if you are in the regime of eternal inflation, then you could start recreating universes because of the stochastic evolution of the inflaton. The only step that I need to think more is if you really go to a temperature higher than the reheating temperature, do you go back to a state with only vacuum energy or not? That at the moment, I'm not 100% sure. You think you do?
You think that inflation started from some very high temperature and then the scalar field got frozen?
I don't know if I have very high temperature, right? I mean, I don't know how inflation starts, but not necessarily by, doing inflation is zero temperature, right? And you could think of, I don't know how it started, but you could just think of some random motion of a field, which then happened to be in a condition with the potential in which they started inflation. Or even with the ideas of Vilenkin, in which you start from real vacuum, in which you have nothing, and you don't even have space-time. Okay, so in a state without space-time, and then you can quantum tunnel into a de Sitter region in space-time. He has done the calculations, and there is a non-zero probability of having a transition from. So what it does, it takes a space, a curved space, and then a closed space, empty, and then he sends the radius to 0. So he finds that there is a tunneling rate between a closed space, completely empty, and the de Sitter space. And the tunneling rate does not depend on the radius. So it does not go to 0 with the radius. I mean, at a certain point depends, but it does not go to 0 with the radius. So then he argues, well, then if I send the radius to 0, what do I get? Nothing, not even space-time. And yet the probability of the quantum transition is non-zero. So you could have, starting from, let's call it nothing, okay? Then you have a quantum tunneling into a tiny de Sitter space region where there is inflation, and that boom, expands, and then the whole story starts. So in that case, there's no high temperature in the beginning at all, okay? So I don't know how it started, and now you want to go backwards in time, and I want to think more, okay, before giving the answer, but it's an interesting question.
And since you mentioned Vilenkin's model, could that happen in our universe?
People have studied that, and the probability is ridiculously small. You know, for him, it wasn't a problem because only he cared is that it's non-zero. Because you have time in the early universe. Okay, you let nothing stay there for a long time, but you know that at a certain moment you can have the probability. The probability that in this room this will happen, okay. So nobody should worry. Okay.
Okay. Any more tough questions for Gian? Yes, this one.
Is it always true that an eternal inflation would always lead to multiple universes, or are there alternatives?
Now there are different. So if you have eternal inflation, so that pattern that I was showing, it will certainly create patches of space-time which are different. They differ, for instance, in in the beginning there is a uniform. There is some vacuum energy, but that vacuum energy is not going to be completely uniform. There will be different patches. So these different patches will expand in different ways. Okay? And then each of them will create universe. So there will be a very dishomogeneous and homogeneous distribution. So in that sense, there is a multiverse. However, then depends what you define by multiverse. If you define by multiverses as regional spaces in which physical parameters are different, then eternal inflation is not sufficient. You have to add another ingredient. And this other ingredient would be, for instance, string theory, but string theory is not the only case. Huh? You can invent a lot of models for producing a multiverse of parameters just using conventional quantum field theory. I mean, as I was explaining, the axion in a sense is a prototype, and so you need an additional elements if you want this kind of complexity that I was talking about. Eternal inflation is not sufficient. You need to have, let's say, 2 ingredients.
Okay, so can we think of a kind of an inflation where, I mean, we do get these multiple universes, but only one remains stable? I mean, say our universe is stable enough to, keep going, but the others somehow.
Actually, people have played with such ideas. People exactly have played with such ideas of justifying our universe by saying that, for instance, find let's call it more or less anthropic bounds on certain parameters by showing that the other universes that do not satisfy certain conditions simply collapse. Collapse because they go into anti-de Sitter, for instance. So it is a possibility. Unfortunately, as mentioned, we are sort of facing this ocean of possibilities, and we have to look for rationales. But the number of branches of possibilities is enormous. And indeed, what you are suggesting was contemplated, at least by some people. So one could use the idea that certain universes collapse, go into anti-de Sitter and then shrink. And that could be a selection mechanism. Because if you wish, one of the problems is to find selection mechanisms that tell you, out of all possible universes, how should I move? Of course, anthropic is one of the possible selection mechanisms, which is a valid one, right? Of saying that in a sense, exactly because we are in a particular universe, we cannot just look at global probabilities, but we have to unfold the global probabilities with the existence of our universe. And that is one selection. What you are suggesting is essentially another one. What I was suggesting in my lecture is yet another one, which is critical.
Thanks a lot.
Okay. No question.
The graph that was there between the complexity, simplicity, and distance. So are the complexity that are arising from the simplicity abrupt or continuous, those complexity?
I'm sorry, you're asking other examples of complexity emerging out of simplicity?
Are there any alternative way that the complexity can arise from those simplicity?
Alternative ways to?
Complexity, like whatever we are seeing in the graph.
Still not sure exactly that I understand.
He was asking when you showed the thing going up.
Yes.
Are there some other ways in which from the simplicity you can get complexity?
Yeah, I mean, at a certain point, I was arguing that that curve maybe keeps on going up and down forever. And the interesting thing is that what happens when we go to very, very small scales, right? I mean, I'm saying, okay, then we reach simplicity. Are we really sure at very small scales, okay, the fundamental theory? We had this picture that, the next step after the standard model is probably a larger symmetry, maybe supersymmetry, guts, and then it's going to strings. And so again, it was continuing this pattern towards simplicity up to really one final point, the final theory, the unique theory that is completely determined by consistency, and that's it. That is still a possibility, but maybe that graph sort of suggested that we could also find surprises when we go to very, very short distances, and maybe this search for simpler and simpler theory will present itself with something totally new and something that goes back into the complexity again. But I have no concrete ideas to suggest. Okay, it's just a thought. Not sure that I replied 100%, but if you wish, maybe then afterwards in private we can continue. Okay.
Okay.
I
So,
didn't completely.
I think
I replied.
I'd like to draw this session to an end, and by thanking Gian for a wonderful talk, all three wonderful talks.
And I want to thank all of you, especially the organizers of this fantastic workshop. It's been wonderful days for me. We learned a lot of physics, and we had a lot of fun, and I met a lot of old friends, and I'm very happy for that. Thank you.